This is Matd1534. We're busy with Unit 11 and we are busy with inequalities. We have looked at the quadratic inequalities and now we're going to look at the rational inequalities. Now remember, the word rational always let us think about a fraction. So that is exactly what it is. So these inequalities are in a fraction way, as we can see here, that we must solve the fraction x plus 2 over x minus 4 less than or equal to 3. So we have already now discussed in the quadratic inequalities that we must be very careful when we do inequalities that we do not multiply with an unknown or divide with an unknown and then the symbol, the less and equal to, is supposed to change. And then we don't. And that is why we still go for this method, which we call the boundary points method. The difference now is that, when we compare to quadratic inequalities, is that we have also now a restriction, because from the outset, x minus 4 cannot be equal to 0. So we are restricted here in the way that x can never be 4. And that we must always start with. So start with your restriction and indicate that x cannot be 4. It's undefined there. Once we have the restriction, we can then go on and do as we said in the quadratic equations, that we're now going to find the boundary points. So we just indicate here that we're going to find the boundary point. And remember, when we find the boundary points, we put the equation equal to 3. And now it's a very simple solving equation because it just becomes linear. And now we may multiply with a common multiple because we know the sign of this common multiple, and it doesn't matter. The sign doesn't matter in this equal equation. So the important thing once again is that we cannot multiply. I just want to go back and just emphasize that we cannot here in the outset, in the question itself, multiply with the x minus 4 throughout, which is our lowest common multiple. Because we do not know the sign, that is what I mean. And if this x minus 4 is negative, we cannot keep the inequality less and equal to. It must then swap to greater and equal to if this is negative. And that is our problem. But when we do the boundary points, we do not have an inequality anymore. And we may multiply with our lowest common multiple. So now we just go ahead and we multiply with the lowest common multiple, or we do our cross multiplication, and then we can find our answer for the boundary point. X is equal to 7 here. Very easy now. Now, very important now, when we now go to the number line, we indicate on this number line the boundary point we just found, but also the restriction we find earlier. So we will have the 7 placed on the number line, which is our restriction, remember, which is always out, can never be included. And depending on the inequality, the boundary point will be inclusive or exclusive. If we go back, we see that we must solve less and equal to 3. Therefore, the 7 will now be inclusive. I made a mistake here. The 7 will now be inclusive because that is the boundary point and the restriction we found earlier. the 4 will be exclusive. And then we will have our three regions here, region 1, region 2, and region 3, that we can test now. And remember, you do not have to show the test. So if I take a number in region 1, say 0, and I placed it in here, I see my fraction becomes now 0 plus 2, 0 minus 4, so minus a half. And minus a half is less than equal to 3. So this is true. Remember, when we test for true or untrue, for true or false, we do the original equation, which is the fraction less than equal to 3. So if my answer on the left hand side, when I substitute x, any x, and the answer there is less than 3, then of course this whole inequality becomes true, because the left hand side is then less than 3. So when I test here in region 1 a number, say the number 0 now, any number in region 1, so I substitute, and when my left hand side is less than 3, it becomes true. So in this case now, we see that in region 1, we find a true region. So meaning all the numbers less than 4 will make that inequality true. If I substitute it into the x, I will have an answer less than 3. When we go to the region 2 and we test for something, any number in region 2, so I took 5, and then when I enter it or substitute it, I see, oops, I do not get less than 3, making this region false. Right, moving to the last region, I can take any number that falls into this region. I took 8, but you can take any number. And when we substitute it, we see that we again find an answer which is less than 3, making this true. So this region then is true again. And then I need to give my final answers, and that is then for the true region. So here I've indicated everything that is true. This was true, and this was true. This is excluded, and this is included. I can indicate it with the square brackets and with a curly bracket, or the little hole here. Let me put the hole there on top that we can see nice and easy. So everything to the left of 4, not inclusive, will be an answer, will be a solution. Everything greater and equal to 7 will be an answer, will be valid, will make the inequality true. So if we answer then finally in set builder form, that will be our answer, x is less than 4 or x is greater than equal to 7. And then remember, if we answer in interval notation, then our solution will be not inclusive for both here, because the 4 is not inclusive, the minus inequality is not inclusive, but the final answer will then be from minus infinity to 4 together with 7, which is inclusive all the way to infinity. Okay, so this concludes now then our rational inequalities, and then in the next video we will look at a practical example.